All right, so as I told the other classes, my bad, the last few days worth of videos had no audio on them, which somebody finally pointed out to me, so that was good. It's weird, they have like 11 views on one of them, but...
I watched it and I just thought it was, you just did it on purpose so we all still felt like we had fun.
Well, that's one interpretation. That could be. Or it could be some like modern art form where you just like draw code on paper for 2 hours, you know.
Sell it for $1 million.
Yeah, yeah.
It's like those YouTube videos that are how to do X, Y, Z, and the whole time the guy's typing what he's saying on
Right,
the screen.
right.
Actually.
Yeah.
Drives me nuts.
Yeah. Or the ones where they don't actually say anything.
Couldn't you have added audio after, like?
I could have, yeah.
But
I wasn't going to go back and repeat.
Yeah.
But you're welcome to make like derivative videos like that. Yeah, yeah. So I think I have it working now. I mean, it's recording now on the right. I have my little sound bar and it's wiggling, so that was not happening before. And I've got a wireless mic on the way. It's going to show up tomorrow, actually, so I might play with it Friday in class. Yeah, so it clips on here, and you wear a belt, and you can act like a rock star, right? So I'm down for that. I thought about that. That would be cool too, but it would be kind of interesting to be standing up here with a headset on, talking to you. I could still wear a fake one, I guess. All right, so so the video should have audio starting today. On Canvas, I opened up an area. It's called Shared Code, and you can bookmark where this takes you. It takes you to a page in my home directory on the Linux server. So twiddlenix/shared, and if you come down under 222, I'm going to start dumping code in here that we go through in class that might be useful. Not a whole lot of stuff, but just if there's something like this one that was the code for building 100 nodes in memory, I thought might be a good example of how we can reuse variables but still get to different nodes, right? So I said I'd post that, so that's posted up there, and you're welcome to browse around in here. There's miscellaneous stuff. There's no telling what you'll find, but mostly research topics. Somebody wanted to see my Twitter feed, so I dumped it out into a PDF. But it's not like an interesting Twitter feed, it's just research results. So I was using that to just send out updates on a project that some people were working with me on. And it was easier than updating a web page. All right, ODP 205-206, any issues with those?
Not really an issue, but I was just kind of wondering, I guess, how you would get to the next node after the setup you pointed to. Like, say it wasn't pointing to my null, so you had a node in between that and the my null node. Like, how would you follow the next field using pointers? Something that was buggy.
So what's the setup we're thinking of?
Like, instead of just 2 nodes, there was the Sentinel node, the node we had in it, and then one other node with data in it after that.
Okay.
Yeah.
So Sentinel, and then these are data nodes. And these are all on the linked list to begin with? Or are you asking about how to add them in?
I was asking how to add the third one in there, so I
Okay.
can get it to actually follow.
So if it's only got one node, it's going to look like this, right? We're going to do this. We're going to do all the algorithms in a few minutes, but let's do this anyway. So you make your new node, call it something like temp, right? So this is a struct node star. And you can malloc. So size of struct node. And then temp, the data field, right, is the thing that temp points to. You want the data field, so you can use this arrow notation, temp arrow data equals 200. That loads that value. And then if you want this previous node, well, you need to have a handle to this, right? Like if you're marching down the list, this might be previous. And we want that to point to our temp node. So we could say previous next equals temp. And then instead of null, this will take on the address of temp. If you wanted to go from the sentinel, right, we could have said sentinel arrow next. Well, sentinel arrow next is this previous node, so we could have said take the next field of that and set it equal to temp. So if you want to insert precisely the second node after the sentinel, that would work. But you can't do that in general, because you can't write code sentinel next, right, for an arbitrary number of nexts. So we do it as a loop instead, and we move a pointer or two through to point to the previous node. So we'll do all those algorithms in detail in a little bit, but that's the basic idea. All right, how's ODP 207? Did we talk about that at all?
Yeah.
Okay.
We ran through all three of them.
Okay. So any issues with that? A lot of people are finding it's easier than they thought it would be.
I think one line.
Yeah, you can do it in one line.
Shall we put some?
All right, well, let's look at algorithms for doing these linked list manipulations using this notion of addresses in memory instead of indexes into an array. Okay, the indexes into the array was kind of an artificial example. Instead of using the whole memory of the system, we used memory from an array of 100 struct nodes. For PA2, we're actually going after just memory locations and putting struct nodes in there and linking them together with the actual memory address. So let me start with kind of our standard setup. And let's start with print, because print's probably pretty straightforward. And let's suppose our sentinel is just list. You can call it sentinel if you want, or LL, or whatever you like. I'm just going to call it list for today. And so this has some fixed data value in it, and let's say that the data in our linked list is 100, 200, 300. And we want to look at our print routine, which takes a single argument, which is a struct node pointer. We can call it whatever we want. It doesn't have to be called list or LL or anything else. It's just a variable, right? So I'm just going to call it, I don't know, I'll call it start. It doesn't matter. Now the idea is the same as what we had before. We want to begin with the first data node, the thing the sentinel points to, print its data value, move to the node that points to, print its data value, move to the node that points to, print its data value, move to the node that points to. Notice that now we're pointing to null, and so we return at that point. If we try to find the data value for null, it's going to seg fault. So we need some kind of temporary variable to take the place of my finger. So we can make a struct node temp, and that's a pointer. Pretty much everything you do, except maybe occasionally when you're initializing, pretty much everything you're going to do with these data structures, you're always going to be using pointers. Okay, it's pretty rare that we're going to actually pass a struct node or set a variable equal to a struct node. It's almost always going to be a pointer to a struct node. I don't know why exactly that is, but it's just the reality. There's probably some metaphysical reason. All right, so temp's going to be a struct node pointer, and we're going to start off with our first data node. So what kind of statement can I write to find the address of this data node? Start arrow next. Right, start is presumably what I'm passing to it, which is the address of the sentinel. Start arrow next says look at the struct node at that address. Look at the next field. That's the address of our first node. So I'm going to set temp equal to that. And on my picture, I'm going to label this temp. So now we're going to loop. So first thing I want to do is print the temp node's data. So print, and again temp arrow data. It says the thing that temp is referring to, look at the data field. That prints the first node's data. And then I want to change temp to look at this node. So what do I assign temp to? Temp arrow next. And on my picture, temp is now here. And I want to go back to the top of my loop. I'm going to print temp arrow data that prints the 200. I'm going to set temp equal to temp arrow next. Now temp is pointing to this node. I'm going to print temp arrow data that prints the 300. I'm going to set temp equal to temp arrow next. Now temp is not referring to a struct node. It's got this magic value null. And that's where I want to give up. Because if I do print temp arrow data and temp is null, I'm going to segfault. It's saying go to the address null, which is a 0. Find a struct node there, print out the data field. Well, memory address 0 is not accessible by design. So I want to exit this loop when temp is equal to null. So a good while statement here is probably while temp is not equal to null.
So is temp the same as next in reference to the last time when we were talking about PA1?
Yeah, I think it's what we were calling next. And then we're just done, so we can return. So check your edge cases. Does it print the first node? Yes. We worked through that. Temp started off at the sentinels next, and we printed this thing's data. That's the first one. Does it print the last one? Yes, we just saw that. Does it work if the list is empty? So suppose our list just looks like this, and this is null. Well, temp's going to start off to be start arrow next. Temp is going to be null. And the first time we check this condition, well, temp is not equal to null, it's going to fail. We kick out of the loop, and we're done. So if there are no nodes, we don't go through the loop at all. That looks good also. So we should be all set. So a few things to keep in mind here. When we write something like temp on top of this block, I'm thinking of temp as being this node, right? But it's not. It's the address of it. It's a pointer to it. So we could actually draw a temp with an arrow pointing here. To me, that gets more confusing. but it's closer to the truth, right? So whatever is making sense for you, that's how you should be drawing your pictures. But it may come out a little different from how I'm drawing them. That's just the way that I eventually started drawing things that clicked for me, way back when. List, sometimes I'll actually draw an arrow going to the sentinel node, but you can also list it as the sentinel node. But because temp is not a node, it's actually an address. That's why we can say things like temp equals temp arrow next, because this is a struct node star, right? It's not a struct node down in this bottom rectangle, it's a struct node star. So if I'm saying temp equals temp arrow next, temp has to be a struct node star also. But I'm drawing it on top of the thing that it's pointing to, basically. Now suppose we had done this. Well, temp arrow next is not null. What's wrong with that?
Isn't it pointing further ahead?
It's pointing further ahead. If I'm thinking of this as temp, I'm asking, is this field null? In other words, is it pointing to nothing? Is this the end of the list? If I were to exit when temp arrow next is null, I'm exiting when I'm about to print the last node. Right, so I would miss it. And if you write this and you run it and it's missing the last node, you might go in and you add something down here which says print temp arrow data to pick up that last node. And then you submit your code and you're done. But you got another problem. Because what happens if my list is empty? I start off temp equals start arrow next, temp is null. As soon as I do this conditional, I'm going to seg fault. If temp is null, I cannot look at temp arrow next. So if you code this up and you run it and it's not doing things just quite right, don't just try to like find something you can add on to take care of the thing that's wrong, right? You really, really want to go back to your original design and figure out what the problem is in there, right? There is a problem somewhere in your process of converting from what I want to have happening into code, right? Assuming that what you wanted to have happen here was correct, figure out where the disconnect was in the code, okay, instead of adding a band-aid. Because as these programs get more and more complex, these algorithms get more and more involved, the worst thing in the world is you're getting a random seg fault every 20th time that you run your program, and you have no idea what your code does, right? You put this in because it looked like it worked, but then this other thing happened, so I added this other piece of code over here, right? Really, really uncomfortable to try to work with that, okay? And I want you to come out of these assignments with a pretty good level of confidence that you understand why your code works, okay? That's going to be important, because each thing that we do is going to kind of build on the concepts that we're using in the prior stuff. So again, good reasons to leave yourself lots of time to immerse yourself in this and then come up for error and so on. Alright, so again, printing is a good one to start with, because you don't have to create anything, you don't have to adjust pointers, you're following the succession of links. But you need to follow those links to do an add, to do a delete, to do a search. So print's a good one to start with. How do you make yourself a linked list? Well, try 3, that code that's posted is an example, right? But you could do something much less fancy. You could just make struct node pointers A, B, and C, malloc space for each of them, set a data value for each one, set A next to equal B, set B next to equal C, set C next to equal null, and you got a linked list, sentinel node to data nodes. And now you can pass that to your print and see if your print works, at least with 2 nodes. And it's good practice, right? Writing those mallocs, writing this next equals that, that's all good practice. That might be your next ODP. I'll probably do that. All right, I'll post an ODP Friday morning. I'll give you Thursday off. All right, I'm posting an ODP where I'm going to ask you to make a linked list with 3 data nodes.
I was just wondering, so this, with this one, it's not gonna be 100 nodes, it'll be as much as memory can allow, right?
Yeah.
Okay.
So there's effectively no limit to how big your linked list can be when you're building it like this. Now, anytime you do malloc, you usually want to check it to see if it returns null. If it returns null, your machine's probably crawling because you're out of heap space. But in theory, right, no problem making millions of nodes, probably making billions of nodes, depending on your hardware setup. Billion might be pushing it.
We all know you aren't going to spend half an hour plugging in a million nodes.
I'm not. I'm not even going to write a script to do it.
It'd probably take more than a half an hour to do
I would write a piece of code to
that. Yeah.
make a input file. But actually, you know the yes command? Yes? When you say yes, it just prints out a bunch of Y's.
Is there no?
No, but you can say yes, no, and then it prints a bunch of no's. So if you have something that constantly wants you to say yes, 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 you know, you sure you want to do this and that and the other thing, and you don't want to keep saying why, you just say yes and you pipe it into whatever it is you're running, and it says yes to everything. Or if you want to say no.
Instead of no, can you say yes and then any other thing?
Yeah, you can say yes,
Pop it over.
this is fun.
Oh, nice.
This is fun.
Well, doesn't it make an infinite loop then? Basically, whatever you give it.
Yeah, yeah. That's a good command. You could pipe it into cowsay, but it would never come back.
What about SO?
Yeah, yeah.
Oh, no.
Just a bunch of training.
Oh boy. Here we go.
Doesn't even look like a train anymore.
Can I
That's
exit?
train.
Yeah. Oh, good, I got out of it. All right, nice. All right, so let's look at other algorithms. As before, I think print's a good one to start with. Let's do delete. So delete struct node, I'll call my argument list this time. So we're going to pass in the address of the sentinel, and here's our data values. We also have to tell it what to delete, so integer num. So let's say we're deleting 200. So we want to take out this node. Well, we can find that node pretty easily. We can start with temp equals list arrow next and see if temp data is 200. If it's not, we can set temp to temp arrow next. Now it's pointing to this node. Is temp arrow data 200? Yes, it is. This is the node we want to delete. Temp is pointing to it. But if that's all we've kept track of, we don't know how to get to this node to change its next field to point to the 300. So we got to use this pair of pointers again. One for a previous, one for a current. So we're going to set this up so that previous is whatever the sentinel node is, which is for us just list. And next is, so if this is previous, how do I find the address of this node? Previous arrow next. Let me call this current. I'm tired of using next. Let's use previous and current. So this is the current node, this is the previous node. So how should I declare those variables? What type of variables are they? Struct node pointers. So struct node star previous comma star current. Alright, so previous is the sentinel, current is the node after the sentinel. And I want to see if current's data is equal to num. So if current arrow data equals num, then I want to delete the current node. Well, let's keep going. Because current data is 100, I'm trying to delete 200. So I want to move previous over here and current over here. So how do I move previous to point to current? It's this simple, previous equals current. Alright, current's the address of this block. Set previous equal to current. Now previous is the address of this block also. So previous is right here. And then I want current to point to the next block. So current equals current next. That moves current here. And then go back to the top of the loop. If current data equals num, yes it does. Right, that's the 200 we're trying to delete. So what do we have to change now? So we're trying to delete current. Alright, so what pointers do we move? Alright, so we want to change previous next so that it points to whatever current is pointing to. Current next. There you go. And there's other things that might seem reasonable for a moment. For example, setting previous equal to current arrow next. Might seem like we're somehow changing that, but we're not, right? Previous is just a variable. Previous doesn't even exist once this delete function returns. So changing the value of previous or current or even list has no effect on the linked list, right? We need to be changing stuff in here or stuff in here. So if we actually want to change the linked list, it's probably going to be some struct node pointer arrow some field that we're assigning a value to. So previous next equals current next sets this to be whatever is here, which is the address of the 300. So now 200 is effectively removed from the list. If we follow the list from the sentinel, we see a 100, we see a 300, we never see that 200. Alright, shall we return at this point?
Free it.
Gotta free it. If you don't free it and you return, it's lost forever. Because the only thing that's pointing to it is current, and once we return, current is a local variable, it's gone. And we can't come back at the end of the program and say, oh yeah, let's free that thing that we deleted. there's no way to get your hands on it, right? You could search all of memory and look for a 200 somewhere and hope that that's your 200, but you're not going to be able to find it like that. So we got to free the thing that current is pointing to, and that's just free current, and then return.
So what do you do if, so we all submit these assignments to you,
Mhm.
and you're running them on your computer, and like you get a couple people that forget to put free in there,
Mm-hmm.
is that just,
It's not a problem because when your program exits, everything gets freed,
oh, okay.
right? So the operating system can say any memory that's been allocated by this process, give it back to the heap, right? And that's easy to do. But we don't have a way to, you know, within our program do the same thing, right? So we can do it by exiting. There might be a way to say free all the memory, but you wouldn't want to do that in the middle of a linked list. But yeah, on Unix, you don't get memory leaks like this once your program exits. On some systems, you might. Different operating systems might actually leave that memory allocated, and then you have to reboot the system eventually. This is more a problem if your program never exits. So if it's doing something like running in the background, waiting for requests, web page requests or whatever, and it's never going to exit, right, these memory leaks will build up over time. And then you have to either kill the process and start it over again or reboot the system. So again, not to pick on Firefox, but some of the earlier versions of Firefox had memory leaks. And if you were in the habit of keeping Firefox open all the time, the performance of your computer would just keep dropping because there was less and less memory. And all you had to do was exit out Firefox, restart it, and everything was great. Mm-hmm. Yeah, Firefox is pretty solid. Well, when it first came out, it was really good because it wasn't Explorer, and it was like, wow.
They had Mozilla, like the precursor browser before that.
Yeah, Netscape. Anybody use Netscape? Okay.
I've heard it.
Netscape since,
Yeah,
I don't even know.
and you can really go back to like Archie and Jughead. That was the pre-World Wide Web days. All right, cool. So this will delete edge cases. If you check ahead of time to make sure that the number you're trying to delete is in your list, so you call search within your delete routine, you'll never have a case where you exit this while loop, right? So this will just be a while forever loop. But if you don't know if the thing you're trying to delete is in your list, so for example, suppose you're trying to delete 2000. Well, you're not going to delete this node, so you'll set previous, and you'll set current, and you'll check 300, that's not 2000, so you'll make this previous, and then current, if this is the end of the list, current will be equal to null. Well, if you go through this loop one more time, you're going to seg fault. Because right here, you're going to check current arrow data, check the data field of the block at location 0 in memory, that's a seg fault. So you would need to do something like while current is not null.
That's assuming you don't check the data.
That's assuming you don't check beforehand. If you do check beforehand, you should never get to this case where current's equal to null. You should find your node before then.
In last PA, you had us write a release node function. It's
Mhm.
going to be important in this, but doesn't free, isn't that what this is?
It's exactly what free does,
Okay.
right? Free is the same as release, so instead of releasing your node here, you just call free.
So I think in my last one, I checked, and I had a while loop like that, so that's redundant.
That's redundant, nothing wrong with that. Right, you gotta while something. And if something changes somewhere down the road and you get rid of that search, right, you got a safety there. And if you're commenting, right, then definitely no harm done. Everything's clear.
And you could just have a final printf statement on the bottom that just says, that number was not found, right?
Yeah.
So if it falls through all that, then that number isn't there.
Mm-hmm. Although usually, so this gets into a bit of a style thing, and this came up in a couple of the submissions. Usually, I would not put a printf in something like this.
Oh,
I would return a flag, right? Give a return value of 0 or 1 or something, so that whoever calls this can decide whether or not they want to check that and print something, right? Otherwise, if you print it here, you can't stop it from printing if you want to work silently. So I would move that to a higher layer. But yeah, if in that case, we could just return here when we exit the while loop. Quick comment back on our print code. So temp was a struct node pointer, and in a lot of cases, whenever we have a struct node pointer, we use a malloc right after we declare it. Right, so we say struct node star something, and then something equals malloc size of whatever it's pointing to. We don't need to do that in here, right? And in fact, it would be pretty glaringly wrong to say temp equals malloc size of struct node, and then immediately after say temp equals start arrow next. Because what are you doing? You're setting temp to point to some block of memory, and then you're changing temp to point to something else. You never use that block of memory. There's no need to malloc it, and in fact, you just created a memory leak. Unless you say temp equals malloc, and then free temp, and then say temp equals start. And then it's kind of clear that there was no reason to do the malloc, because you malloced and you freed right away. So, but we kind of get into this habit of mallocing when we have pointers, but I don't want you to think that you always have to do that, right? You do that if you're trying to create a new block of memory, which we're going to do with add next. But if we just want something that can point to a struct node, we can just declare it to be a struct node star, and then we can assign it values of other things that are struct node stars. Oh yeah, other edge case to check for delete. Does it work if you're deleting the first node? So if we're deleting 100, we're going to start off previous is here, current is here. If current arrow data equals num, which it does, what do? We take previous next and we set it to current next. So the sentinel's next will now point to whatever this was pointing to, which is 200. All we've done is change the sentinel to point to 200 instead of 100. That's a good delete. So it works in the case of deleting the first node. That's really the only edge case to worry about. Towards the end of the second hour, I want to run through these algorithms and look at what happens if we don't have a sentinel node, just for kind of comparison's sake. And when we switch to binary trees in a few weeks, we won't have sentinel nodes on trees. So some of that will come back in a meaningful way. So let's do our add. I'll call it LL this time. It's a favorite picture. And let's add 150. So we're going in between these two nodes. All right, so same thing as before. We're going to want a pair of pointers, previous and current. So this is LL. This is also previous. So previous equals the sentinel, and current equals what the previous points to. So that's our setup. And again, we're going to use this inequality. We're going to compare the current node's data to the value we're adding. If this is smaller, then we're going to add after this node. Right? If this node has a value that's smaller than what we're adding, since we want this in increasing order, we're not going to insert before this point. We're going to insert somewhere after. So if current data is less than num, so I'm doing this in the backwards order from how we did it for PA1. That's intentional. So move down the list. So we want previous to be here, we want current to be here. So same as when we were doing delete. Previous equals current. Current equals current next. Now I can do an else statement here. I could say close bracket else, and then I could list the code for inserting our data. That's how I would probably do it. But we could also say continue, and continue takes you back to the top of whatever loop you're sitting inside. The advantage of doing continue is everything over here I would not have to indent. Right? It would just be the block that was executing if I didn't execute this if statement. But I'm going to do an else. So our else says, well, let's loop back up to the top once. So previous equals current, puts previous right here. Current equals current next, puts current right here. And I'm going to skip the else statement, so I'll come back up here. This is all going to be inside a loop. So if current data is less than num, so current data is 200, is that less than 150? No. So I'm not going to move down the list. So I'm going to do my else part. So at this point, I'm inserting 150. Where do I want it relative to previous and current? After previous and before current. Insert after previous, before current. So right in between. All right, got to make a new node. We got to sandwich it in between these two nodes. So I'm going to need a temporary node. So I'll do a struct node star temp. And how do we make a new node? Malloc. And size of parentheses struct node. Don't do struct node star. Okay, that's always going to come back with 8. So size of a struct node, that's what we're going to point to. So malloc size of struct node. So now temp is just kind of hanging out somewhere in memory, and it's referring to a struct node. Well, we're adding num, so we want num to go into this node. So how do we set the data field of this to be equal to num? Temp arrow data equals num. That loads the 150 right there. And now, how do our pointers change? This
Previous arrow next equals 10.
So previous arrow next equals temp. So our previous, instead of pointing to current, points to temp. Good. So now the previous node is followed by our new node, which should be followed by current, right? So how do we make temp point to current?
Temp arrow next equals current.
There you go. So now this points to current. good to go. Do I want a free temp? No. If I free temp, this block goes away, and when I start following links, who knows what I'm going to find here. Okay, temp's part of our list, so we're going to keep that. The variable temp will get disposed of when I exit from this function, right? But the thing that it points to in memory remains intact. But temp itself is local, so the value of temp is meaningless once I exit. But the thing at the value that it had is still intact in memory.
So in program 1, I was able to, you go get the node.
Mm-hmm.
Actually, I think I searched first if the number was in the list, but
Okay.
you get the node, and then instead of looping through and having it do like assign temp to that node and make it valid, I just did it once outside.
Mm-hmm.
But in this case, if you do that and then you end up not doing the whole process, you would need to free then at the,
Right.
at the end.
Same thing in PA1 though. If you allocate, if you got a node and you set the valid flag to 1, you didn't end up using that as part of your list, you needed to go through and set that valid flag back to 0. Otherwise, you've used up a space in your array that's not actually being used, which means it's never going to be deleted, which means that's never going to go back to a 0. So it's kind of exactly the same situation that we have here. But yeah, we could do the malloc in the very beginning as long as we know we're going to add. We've already searched and it's not in the list. We could do the malloc right in the beginning. We could set the data value right in the beginning and then just adjust the previous and temp pointers. Alright, so at this point we can return. So we're marching through. If we're not ready to insert, we just adjust our pointers to go to the next node. Otherwise, we make a new node, load the data, adjust the pointers, and we exit. And this whole thing is a loop. But that's going to probably end, but not necessarily. So what happens if we were adding 450, I know you can't see that, but we wanted to add 450 to our list? Well, we're not going to have done any of this stuff. Previous and current, we check current. Current's data is less than 450, so we're going to adjust the pointers again. We're going to set previous here, and we would set current to, and let's say this is the end of the list, we would set current to whatever its next field is, which means current is going to be null. And if we go back to the top of the loop, when we say current arrow data, we seg fault. So we want to loop, and we want to do it while current is not null. So if we come out of the loop down here, what do we know? We know that we got all the way to the end of the list and we still didn't have a place to insert our new node. In other words, our node's data value is bigger than everything in the list. This is an edge case. So we want to add new node to the end of the list, which is immediately after previous. So malloc a new node, which we can call temp, same thing that we already did, right? So struct node star temp equals malloc size of, temp data equals num. What's the pointer? Magic in this case. So we want to tack this on to the end of the list. The list ended here, and this was previous.
previous next equals 10.
Temp data equals nil.
No, current next equals 10.
So previous next equals temp takes this and has it point to temp. So we've tacked it onto the list.
And it's just temp next equals nil.
And then we need to take care of this. So temp next.
Well, and data too.
And the data, yeah. Temp next equals null. And I'll put it in there just to be complete. Temp data equals num. And it's an edge case, but not really, because what did we do before? Temp arrow data equals num. We did that in both cases. Previous arrow next equals temp. We did that in both cases. Here we said temp arrow next equals current. Here we said temp arrow next equals null. But current's equal to null. So we could have said temp arrow next equals current, and it would have set it equal to null. So it's the same three statements, they're just happening outside the loop.
So, is there a way you could structure your if so that it would catch that?
There probably is, but do that after it works. That's a fun exercise, I think. All right. Making sense? Clicking? And search we probably don't have to go through because it's just like print, but instead of printing you just check to see if the data value equals your number. And if it does, you return. If you get to the end of your while loop, then you never returned, so you didn't find your number, so you return not found. Right, but it has the same structure as the print routine. The trick again is just sort of marching through the list, looking node by node.
So assuming you did a search beforehand, so you didn't have to deal with like print messages and the side function. If you got to the while loop and didn't return, and you got to the end of it and you never returned, like is there a point at which you return a 0 instead of a 1?
For search?
Yeah.
Yeah.
Oh no, for add, like if you
For
did
an
your
add?
search beforehand, like is there any point in returning 0? Because assuming like you're
For add, you're always going to add your number to the list, right? If it's bigger than everything, you add it to the end. If it's smaller than everything, you add it to the beginning.
I mean, assuming like you built a linked list of a fixed size and it just didn't find any room for it or something.
So that's the
Memory's
only
different.
possible exception is when you try to create a new node, you're out of memory. So that would be the only thing I'd return from add.
I'm assuming if you did like malloc, it wouldn't be able to find anything and it would give you an error.
Yeah, so malloc will return null if you're out of memory. So in here, whenever you do malloc, right up here or down here, you check temp, and if it's equal to null, you're out of memory. You can't add. So I would return a 0 at that point,
Yeah.
right? Or whatever the assignment said to return
That would be like
if
an
you
extreme
failed.
edge case.
Yeah, yeah. And you're probably not going to be around long enough to see it because your system's going to be crashing.
What about duplicates?
So your search can handle that ahead of time, but if you don't search ahead of time, this will seamlessly insert duplicates, right? Depending on whether you do a less than or equal to. With a less than, it would insert a 200 after this node, right? And that's perfectly fine. When you try to delete, it'll delete the first one it finds. When you try to search, it'll return if any of them are in there. So you can do duplicates in this, but we haven't really defined what it should do at a higher level, so that's why I said no dupes. So,
Okay.
and
That would be,
yeah.
that would be like something where you would return like an error.
Yeah, so you could return an error code saying that you can't insert, it's already in there. And I don't remember what I spec'd out in PA2 for the return codes, but I do have it printed out so I can find it quickly actually. So add returns 1 if it's successful, 0 if there's no space left in the array. So add is assuming that you're not adding something that's already in there. Yeah, but this part was the same. So, but you could return -1 if you find a duplicate or something like that. I don't care if you add to this specification. Delete returns 1 if it's deleted, 0 if it wasn't found. So these are all horribly inconsistent, but that's okay. and you're not writing get node because that's malloc, you're not writing release node because that's free. So, and I think those are the only things that returned values. Oh, and search just returns 1 if it's found and 0 if it's not. So I'll tell you what I told the last class. You know enough to be able to do PA2 at this point, right? There's a good chance you could knock out all these functions in a few hours if you really kind of like get in the zone and just start chowing on it. This is where these programming assignments start to get the nature of problems that you really want to kind of like set aside a few hours at least and get yourself a good environment. That might be music, it might be food, it might be whatever. But get yourself a good environment where you feel like you can kind of get your head into this problem and not have to come up for a few hours. And these assignments work really well in that way because you got all this stuff, and while you're writing it and you're working with the pictures and you're updating things on your side paper and so on, all that's going to be in your head, right? You're going to look at this, you're going to know what previous is, you're going to know what temp is, and so on. As soon as you come up for air and you go away for an hour and come back, it's going to look like this, right? And if I just gave you this and said, tell me what this does, right, that would be cruel, right? This stuff is much easier to write than it is to read. So commenting will help, right? And enough experience with this will start to, you'll see things like this and you'll recognize it and say, okay, I'm inserting something between nodes. But for doing PA2, if you can afford the time and the environment to really kind of like sink yourself into it, it can be a really good, productive experience, okay? Modulo whatever real life brings your way, whatever the realities of your situation are when you're working on code. But the more you can do that, the better, up to a point, okay? Now, if you're pounding on this for 12 hours and you're not getting anywhere and your code's not compiling anymore, right, you probably should have taken a break several hours earlier, okay? Because there is a point where everything starts to blur and you start making silly mistakes and you forget things that you already knew how to do. And if you can recognize that point, right, take a break. Go out and walk or work on something else, do some relaxing physics homework, maybe something. And then come back to it, okay? Or if you get to a breaking point, you've been working on print and working on it, and it finally works and you understand what it's doing, right, that's a good breaking point. Right, go away, let that settle for a while in your brain, maybe come back the next day, start working on delete, right? So this can be really, really complex and confusing, okay? But at some point it will click and you'll see this sort of direct connection between what you want to do, how these pointers change and so on, and what the code is that you write to do that. And when you reach that point, then, right, sky's the limit. You can do anything in data structures, and we're working with trees and tries and hashes and stacks and queues and all this other stuff, and it'll just be using this machinery. And it's actually a lot of fun. Once you've got a good command of these tools, then using them in all these different ways is kind of a fun puzzle solving thing. So definitely start early, right? Not the Thursday before, but one of the next few nights or this weekend or something, or sometime if you have a chance to sort of sink your teeth into this. It should go pretty well. I was going to snap that. All right, let's do a 5-minute break. Let's come back at like 7 after the hour. And let's talk about some other aspects of lists.
I'm not sure if you want to take a screenshot of that, but you kind of moved it up before you took the picture.
Yeah, that was deliberate, because
Oh, okay.
I'd already taken one before
Oh.
we made those last changes, so then I moved it up so I could write all the way to the bottom.